My name is Kyle Schwartz. I'm a software team lead here at Intrepid Control Systems. I'm a team lead for the Vehicles by X team, which oversees LibICS Neo, Socket CAN, some of our cross-platform options. And my talk is going to be on Python for ECU design and testing. So how we can leverage Python for the entire ecosystem for ECU design and testing. So probably the first question is, why Python? This might be obvious to a lot of people, but Python is really taking over the programming world by storm here. It's widely used in automotive already. There's a large talent pool that allows you to basically always find new people that can quickly pick up on it, and there's probably quite a few people in your company already that are already pretty familiar with it. It's easy to learn, so you can have non-engineers pick up Python and start writing ECU code, or they can start writing tests against the ECU. But it's so easy to pick up that pretty much everybody can start taking a hands-on approach to ECU design. So another huge benefit is that it easily translates into C and C++. So you can do rapid prototyping with Python, and then you can transpile it into something like C, and then your ECU code is halfway written. You probably have to do some security checks on it, make sure that you conform with anything, but you're most of the way there just by mocking it up in Python and getting most of the logic set, and then you can just transpile it and get a good baseline. Since it's so high level, it's basically like writing pseudocode. So you can quickly iterate on the logic for an ECU or a test or what have you. You just it's so easy to pick up on, and since it's such a high level language, it's basically like writing pseudocode anyway. So we really embrace Python here at ICS. We use it internally for our hardware testing. We found that it really reduced our tester complexity for all of Intrepid's hardware. And since using it, we found that actually a lot of teams can kind of jump on our tester repo and commit changes that they might have found with our hardware. So you can actually have the added benefit of other teams just kind of cross-collaborating because Python is just so easy to pick up on, and just get the benefits for that testing repo from across the entire company. And here at Intrepid, we use a lot of external packages for Python. There's such a large variety of useful packages that everything from like ODX to LDF. There's probably a package already made for what you want to do that's open source and publicly available. So that's kind of the internal side for Python, but we also offer two prominent Python libraries. So Vehicles by X, which I'm the team lead for, and then Python ICS, which is just a hardware I/O library. But both of these provide a Python binding and API. So I just want to talk about some quick Vehicles by X highlights. So it's cross-platform. It runs natively on Windows, Mac OS, and Linux, and on Linux it'll run on ARM 32 and 64. It'll also run on M1 Mac. We can open most of your prominent databases, ARXMLs, DVCs, VS3s, VSDBs. We're adding support for ODX, for MDF. There are quite a few Python features that I want to kind of highlight here, but as a core principle for X, everything that we do on the C++ core side, we actually automatically generate bindings for that are just exposed through the Python interface. So if we add a new feature to the C++ core, you'll just automatically see it from the Python side. So we have ECU simulation as part of the Python interface. We have reporting, so you can generate like HTML reports for signal data. We have a full diagnostic stack for UDS over CAN and DOI. And I kind of want to highlight a couple of the GUI features. We have a monitoring view, so you can kind of see the signals come in, do some filtering on them. We have a plotting library, so you see the signals go up and down. And we have database browsing. So after you import a database, it'll create a bunch of objects in Vehicle Spy X. And after it's been imported, you can go ahead and just browse the objects that were created for our database browser. So it can kind of give you a really good insight as to what the database actually contained. So here's the monitor view. You'll see on the left side here the first blue box there is the level filter. So this allows you to decide which level you want the main row for the primary monitor view to be displaying here. So if you lower this level, you'll actually see deeper into the PDU by default. So this really allows you to drill in as far as you want on each of the PDUs, and then you can work your way back up the stack if you want to. We also have full custom filters. I won't cover them too much in depth because they're incredibly powerful, but you can do signal values, you can do actively changing a number of different custom filters. You can do and or logic with all of these, and then you can combine them to make a really advanced custom filter. And then when you save your vSpy-X save, it'll actually save those filters and you can load them in so somebody else can see the same thing that you did. And then we have standard filters. This is familiar probably for anyone that's used vSpy free. So we have the classic transmit. This is include, exclude, and errors changing, no match. We also have channel filtering. So if you wanted to maybe show or hide a specific channel, you can do that just by clicking the little eye, and it will either show or hide it. And then one more filter that we have is column filters. So this is on the top here. So if you just start typing in any of those columns, it'll actually drill into the data that's being displayed and go ahead and filter based on that. And then really the main part here is the actual monitor view. So you can see the signals are highlighting as they change. This is just a replay that's happening and it's on loop. So we actually have a demo out there if you want to take a peek. It's basically doing the same thing. Another view that I wanted to focus on is the signal plot. So here you can see just the RPM signal for this replay that we were doing. So you can actually do multiple signals. I'm just showing one here, but if you add more, it'll just stack them on top of each other. And then here's the topology view. This is what you're going to be presented with first. So when you open vSpy-X, this is the first thing you'll see. And the big blue button that you see down in the bottom right is basically the entry point for everything. So you click on that, you can add your database and buffers there. And then they will generate elements within this topology view. So if you see the second row here with all these boxes, this actually came from a database. So after you load the database, these will be populated. That first big box there is actually a physical piece of hardware. So that's a Fire 2 after it's been activated. So after you activate the hardware, you're presented with a bunch of these little bubbles on the bottom of the hardware, and you can connect these to the actual database elements like the CAN clusters, and that actually drives the entire configuration for the topology after that point. So if you enable ECU simulation at that point, it will follow the rules that you did during your drag and drop for these lines here. Okay, so outside of the GUI interface, we have the Python interface, and Vehicle Spy X is probably much more powerful from the Python interface at this time. So I'm going to cover basically the interface that everyone would use for every Vehicle Spy X script. So first line is going to be import vSpy-X. That's pretty basic. That just loads the vSpy-X module. And then the next one creates a new application. So this is like the primary object for all the state. And then you can add a database. Just give it a path. You don't have to say add ARXML. You can just give it an ARXML path or a DVC path. And then that will actually create all the internal objects. And then at that point, you could start querying them with our resolver. So our resolver is basically a tree within Vehicle Spy X. that contains kind of the nitty-gritties for how the database was loaded. So if anyone is familiar with the ARXMLs here, they cross-link between each other a lot. And this resolver is our solution to that. So if you want to query the resolver and do a URL lookup, like you would see in an ARXML, you can do that right here. And the object that's returned, you can use it in other parts of your script, but this is primarily used to find like signals, ECUs, clusters, you name it. So, and then add source. So this one, it adds not just a buffer, but also it could be hardware. So the same interface for both. There's a special API for hardware that we have documented that I didn't show here, but if it's just a replay, you would just add the BSB here. But if it was hardware itself, you would give that hardware identifier, and then it would behave the exact same. So important to note here is that a source in our mind, it could be a replay, but it could also be a physical Intrepid piece of hardware. And there's no distinction as to how these are handled in Vehicle Spy's core. So just kind of continuing on here a little bit. So for ECU simulation, you have to enable the mode for the ECU to be active. So this basically says that after this mode has been set, once you go online and start the application, that it will just start transmitting canned data onto the bus. So it's like all zeros or the default value, enum 0. But basically, this just says, okay, the ECU is going to go into an active mode, and once we go online, it will actually start simulating. And the next one here is the on point. So this is probably the most important of all of them. So the on point allows you to hand the observer, which is like a all-seeing, it's like a tap for everything. It allows you to hand it a callback for every single point that happens in the system. So this could be a signal, this could be a TCP frame, this could be an Ethernet frame. So you get to decide the level that you want to drill in on, but this point callback will be hit every single time a point comes in. And in your on point, you can do all the logic that you want. You can have complex simulations happen here. You can mutate the data that came in. It's really up to you. And then the next one is the Vehicle Spy start. This just does final linking, activates the hardware, and actually starts Vehicle Spy X. After you're online, for ECU simulation, you would use our set signal. So this is how you update the cache value for the signal. So because it's ECU simulation, we cache the value that you set, and then on the proper timing, we actually transmit it. So you're not directly transmitting it. It will save it, and then the next time that the ECU is supposed to behave as if it was transmitting, it will go ahead and do that with the value that you set. Okay, so Vehicle Spy X really has some interesting use cases with our Neobi Pi. So our Neobi Pi, for those that aren't familiar, it's a Raspberry Pi Compute Module 4, and it's basically that with a ValueCan 4 hooked up to it. So you have the industrial CAN side for our ValueCan hooked up to the full Linux development environment for a Raspberry Pi. So this is a really cool platform because you can do things like utilize the full Linux environment on here. It has 4 CAN FD channels, but for this application, you could do something like VS Code remote SSH here. So you could do ECU development on the Neobi Pi with the remote SSH extension with VS Code from anywhere. So you can have your VS Code open, you can debug your Python script, and all of this is actually happening on the Neobi Pi itself, which is transmitting on CAN. So it unlocks some really interesting development cycles here. You can do full Python debugging, and you could even do like pair programming with multiple people for this ECU simulation design. Another really interesting one is Vehicle Spy X and the ValueCan 4 Industrial. So This is kind of a value can 4 that's specifically designed for like end-of-line testers. So its real selling features are that it has 2 galvanically isolated CAN-FE channels. It has a single galvanically isolated LIN channel, and it also has a DIN rail. So if you pair this with Vehicles by X, you can essentially replace ECUs in end-of-line testing. So Vehicles by X would talk to the value can 4 industrial and could act as an ECU in that end-of-line tester environment. And then you don't have to have a physical ECU there. You can just iterate on that ECU model in Vehicles by X. So this really reduces the complexity and cost. And you can do UDS and ECU simulation with one product this way. Because we have a full diagnostic stack, you would have a single script that might do UDS initialization, and then after the ECU is in some known state, then you could maybe start doing ECU simulation against it. So we actually have customers that are doing this right now. It's a great way to get rid of those end-of-line testing ECUs and start actually using a more virtual way to do this. So we can do REST bus or a single ECU. It's really up to you how much you want to simulate for the network. After you load in the ARXML, we can simulate the entire thing for if you'd like, or we can just simulate a single ECU. So Vehicles by X really has a lot of functionality in that regard. And because Python is so easy to pick up, this really can kind of move that testing writing back into technicians instead of requiring it to be in the engineers. So there's now this closed loop where you can have just people that are working on this ECU simulation testing design that don't have to have an intimate understanding for the underlying ECU code that actually was used to create it. So one more thing here is ECU simulation for fuzzing. So probably most people here are familiar with fuzzing. It's basically the act of putting a bunch of pseudo-random, or it could even be purely random if you're logging data onto the bus in the hopes that you will trigger an unexpected event in a given ECU on the bus. And if you have more intelligence to actually drive that fuzzing, you can make better guesses as to how to break things. So by doing ECU simulation here, it's much more robust, and you can actually transmit with like the proper timings just with that data, or just slightly modulated data, but it still behaves like an actual ECU. It's just like an ECU that's misbehaving. And you can also do things like react to inbound data. So you could be listening on the bus, and then maybe you want to modulate one of the signals that came in, and then see if the bus reacts appropriately if you send it back. So that kind of thing. Oh, you can also trigger on specific inputs. So one other great resource that we have for Python at Intrepid is our Python ICS library. So this is a fully open source Python wrapper for our ICS Neo 40 DLL. So it has the full power to communicate with any of Intrepid's hardware. And then it provides a nice Python interface for you. So this works on any platform. And if you're on something other than Windows, like if you're on Mac OS or Linux, it'll actually use libics Neo for the underlying device communication. So you can have a full open source stack for device I/O. And this is really great for database-less workloads. So if you don't need to have a full understanding for what's going on the bus and you just want to send CAN messages, you can do that with Python ICS. And it's a really straightforward workflow. So I just want to cover the quick API here. It's so straightforward. I won't talk into it very much, but the first one is just you can find all the devices. You open it, and then you can create a SPI message and populate each of the fields for This one is an HSCAN message, and then you go ahead and transmit it for the specific device that you open. And then the last one is to get the messages for the device. Okay, so Python is really a great tool that I think is underutilized in automotive, and I think it can really be used a lot more for ECU design and testing. I think we've used it successfully here at Intrepid for hardware testing, and I think it has a place in testing automotive ECUs at production grade here. So it really can reduce the cost of those late stage bugs by catching them much earlier, because you can iterate on that test and you know, change your entire model without having to recompile and reflash and have this, you know, this arduous process to actually just update your test. And it's just it allows many people from your companies to come and help with different things. So you will find that if you start opening up these APIs for these complex tasks, that people from other departments will actually be able to help contribute fixes to them. We found this with our testers internally at ICS. And really, this can't be understated how helpful it is that Python provides just a vast collection of libraries that can get you up and running immediately. There's unit test, there's matplotlib, there's NumPy, there's so many Python libraries that you can use that enable your workflows, and there's even specific automotive ones that are available for free that you can probably find if you just look for them.